Hello, everyone. In this lecture, we're going to talk about three distributions: chi-square distribution, t-distribution, and f-distribution. The first one we're going to discuss is the chi-square distribution. So before we talk about chi-square distribution, let's first have a look at it. If we have a standard normal distribution, okay? And standard normal distribution is z, and we use the notation z, and that is normally distributed with mean 0 and the variance 1. So if z1, z to zk, they are independent, normally distributed random variables with mean 0, variance 1, then the sum of the squares of zi, it will become chi-square distribution. So we sum of the k standard normal random variable together and the square of them. This will become the chi-square distribution with k degree of freedom. So the parameter k is a positive integer that specifies the number of degree of freedoms. That is also the number of independent zi's. We sum the square together. So if we have, you see here, this is a normal distribution. And based on the central limit theorem, we know that x bar, the variance gets smaller. Okay, so x bar is the sample mean. Now, if we calculate the statistic error, so we know the error is each sample from the population mean, and the residue is from the sample mean. So the major difference is right here, okay? So epsilon I hat is the estimation of the epsilon I. So that's why we put a hat over there. The sum of the squares of the statistic errors divided by sigma square has a chi-square distribution with n degree of freedom. So suppose in this sample, we have n observations, okay? And then as you can see, sum of the squares of n statistic errors divided by sigma square. Then if we put this arrow in the parentheses, we got this is xi minus mu. Then we put it inside. This is actually the standardization. You see, this part is the standardization because z equals to x minus mu over sigma. So we have the sum of the squares of n standard random variables, okay? Independent zi's, the square of independent zi's. So now, previously we summed the k of them. Now we sum n of them. So this will become the chi-square distribution of n degree of freedom. But this is not observable because many times we don't know the population mean. Okay. Now, but we can calculate the sum of squares of the statistic residues. Okay. Now, for the residues, okay, the residues, we just lost 1 degree of freedom. Okay, although this is not observable. But if you sum the, if you sum I equals to 1 to n epsilon I hat, this is the residues square divided by sigma square. This is actually chi-square distributed with n minus 1 degree of freedom. You just lost the 1 degree of freedom. So chi-square distribution, this is the shape of the chi-square distribution. Chi-square R for n, so n denotes the degree of freedom. Alpha denotes, okay, the upper percentile, the how many is actually the shaded area, okay, and this is alpha. You can have chi-square 0.05 and 10, so that means you have only 5% left in the whole area on the curve, and 10 degree of freedom. This will be 18.307. And on the other hand, on this side, chi-square 0.95. That means you have 5% left over here. And then the right-tailed means from here, this is a left-tailed, this is a right-tailed. Everything to the right is about 90%, 95% left. Everything to the left is about 5% left. So for example, here, you have 5% left to the right and 95% left to the left. But here you have 5% to the left and 95% on the right. So this is our two critical points. So this one represents the areas you have here under the curve. And this is a degree of freedom. And this is a location. Okay, this is a location, chi-square 0.0510. This is a location right here. Okay. Okay, that means if the right-tail probability is smaller, the location will be bigger because you want to push it to this end, right? So this is a chi-square distribution. Now let's move on to the t-distribution. So for t-distribution, if you have x1, x2, xn, that is normally distributed with mu sigma square, we know that this is a central limit theorem. Okay. As I said, this is the most important theorem in statistics and probability theory. So that's why you see everything that we are talking about, they are all based on the central limit theorem. So X bar is approximately normally distributed with mean mu and sigma square over n, the variance getting smaller. And now we do the standardization or normalization. Then z equals to X bar minus mu, sigma over square root of n. This is normally distributed with 0 and 1. However, if you replace this sigma, you see here, the only difference is you replace this sigma with s, okay? Then this will become t distribution with n minus 1 degree of freedom, okay? So T alpha k is the value of random variable t with k degree of freedoms, above which we find an area, alpha. So also an upper tail, okay? An upper tail 100 alpha percent point of the t distribution with k degree of freedoms. Again, if you keep sigma over here, you got a z. If you have replaced sigma with s, you got a t distribution. If you are in a t distribution, you will have alpha and the k, okay? Because we want to know what is the degree of freedom. Because when you calculate the sample standard deviation, you actually use the n observation or n data points. So we want to know how large did you use. So that's why we need to know n. Okay, now let's move on to the now. If you have the T1, this is a T distribution. T distribution is approximate, is also symmetric, very similar to the normal distribution like this. Okay, and oh, I didn't do it right. Let me. Okay. Now you have T1 minus alpha k, and which is actually equals to, so you have 0 right here. Okay, and T1 minus alpha k is equals to minus T alpha k. So you could have upper tail, you have 2.5% left and 21 degree of freedom. That means you use the 22 data points to calculate the sample standard deviation. Okay, then if that is the case, then you will have 2.08. You can check the table or use any other approach to do that. Okay. Now, if you know T.02521, of course you know T.97521 because they are symmetric. Okay, so this is a discussion we have so far Now that's about T distribution. Let's move on to the last distribution we're going to discuss in this lecture. That is called F distribution. So F distribution is compare the ratio between the two independent chi-square, because you got a residues, right? Residues, they are chi-squarely distributed if you divide by sigma, right? And then you want to compare the sum of the squares of the residues, which one is bigger. So that's why we need a F distribution. So suppose we have W and Y, both of them are independent chi-square distribution, but with different degree of freedom, U and V degree of freedom. Then the ratio, you see the ratio. This ratio here, F is W over U and Y over V. This is the F distribution with U and the V degree of freedom. So what is the U? U is the degree of freedom in the denominator, and V is the degree of freedom in the, U is the numerator. V is the degree of freedom in the denominator. You gotta make sure you use Y and divide by its corresponding degree of freedom, okay? We cannot just divide by other random variables degree of freedom, because this one has the corresponding degree of freedom. This one has a corresponding degree of freedom. Then we use W over U and Y over V. Okay, and then this will become the F distribution with U and V degree of freedom. So F distribution, we could also have upper tail alpha left, and this will be F alpha UV, and this will become F1 minus alpha, because everything to the right is 1 minus alpha UV. We always use an upper tail. So F.05, 10, and 6. This is 4.06. This is only 5% left. So this location is 4.06. However, if you know one of them, if you know F alpha UV, you also know F1 minus alpha UV. Okay. In other hands, because F equals to W over U over Y over V, if you switch the denominator and numerator, then the degree of freedom will switch. So that's why you see here, F, the theorem here is F1 minus alpha, U and V equals to 1 over F alpha, but this is V and U, okay? You see, we shifted this numerator and denominator degree of freedom because we are taking a ratio 1 over. So we flip the sign. We flip the numerator and denominator degree of freedom. So in other words, if you have F.95, 6, and 10, this will become, this will equals to F.05, 10, and 6. So we know this 10, and 6, this is 4.06, then this will become 0.246. But if you want to know F.95, 10, and 6, then you will have to get F.05, 6, and 10. Okay, but we don't have this number here. But you can always check the probability table or use the computer software to get this value. Okay, we have separate lectures on how to use the Excel to get those numbers, or you can check the how to check the statistic tables to get those values. And those will be available in the later lectures. So far in this lecture, we have discussed the first one is the, let's see, the chi-square distribution. And then we talk about the T distribution. And then the last one is the F distribution. Hopefully this lecture will give you a better idea how those distributions are defined. And we can have a look at more examples later and on how to utilize those distributions in regression or in the design experiments. So those distributions are very critical to later chapters. So that's why I want to give you guys some ideas about those fundamentals first before we move on to advanced concepts. Okay, so this is the end of this lecture. Thank you.